now move to topic 25, which will be the focus for today. Okay, so let me, okay, all right. Okay, so we talked about regression, okay, in the nearest neighbor prediction, and the term wide is regression, and the graph that we have seen how the prediction is done, okay. And in this topic, we are covering linear regression, okay. Notice that we add a term linear in front of regression, okay. So it's gonna be a form of regression. You're gonna see that it's gonna regress to the mean, okay. But it's gonna regress to the mean in a very specific way. And we call it linear because as you'll see that there is a linear relationship as how we are constructing the regression line, okay. So the basic stuff, okay, is regression to the mean, like I said, okay. The regression line, the linear regression line that we're gonna present, okay, and you're gonna model is a statement about X and Y pairs, okay. So you have two continuous, okay, numerical variables, okay, and then this linear regression line, you can think of it as a statement about X and Y pairs. And in particular, okay, there's some subtlety here, okay. We try to, in order to interpret this regression line, it is always good to measure X and Y in standard units. Okay, so now if you remember a couple of lectures ago, we talked about standard units. Okay, so for any observation, like a set of data value, okay, for one variable, you can standardize it, okay, by subtracting the mean from it and divide it by standard deviation. Okay, so in that way, we're able to get rid of the units, you know, like say put different variables on the same scale. Okay, X and Y, like say X in that golden example is the parent's height, right? And then Y is the child's height. So in that case, maybe not too bad in terms of the units, you know, they're all inches, okay? But still they have different ranges, okay? So for us, we want to standardize them so they're all on the same scale, okay? And it's much easier to interpret the linear regression line when we do that. So bear with me, let's keep that for now, and then we can come back to the original units and then see how that affects, like say, you know, the units themselves, how they affect the how they affect our interpretation of the line. All right, so if we now measure X and Y in standard units in their own, okay, and what this regression to the mean, the linear regression that we're doing here, is describing the deviation of X from 0 and the deviation of Y from 0. And here we focus on 0 because once we do the standardization, right, the mean of the new X's in their standard units is going to be 0. Okay, and the same goes for Y as well. So if you think about now deviation of the X and Y from their mean, they are pretty much X from 0 and Y from 0. Okay, so really, whenever we're doing this kind of regression, we're trying to explain the deviation of Y from 0 in terms of the deviation of X. Okay, and imagine like those kind of plot that we have seen, right? Like it's scattered around, and then if you look at one particular record, you have the X-axis and the Y-axis. Okay, what we're trying to say is that if you're going to standardize both pairs, the X and Y's in their standard units, then the linear regression line is trying to describe how deviation of Y can be explained by deviation of X. Okay, if a lot of that deviation of Y can be explained by the deviation of X, then you might see that, okay, the prediction or the linear regression will be fitted pretty well. And also the prediction could be very accurate. Okay, but however, sometimes you might have scenarios where linear regression might not work well. And then that will be the case that you will see that the deviation of Y might not be really well explained by the deviation of X. Okay, so whenever we're trying to use a predictor, imagine, okay, and even just in daily, I guess in daily life, if I look at outside of my window, I'm wondering, okay, whether it's going to rain or not, right? So you're thinking about making prediction using the information that you have, okay? And then you want to use good predictors, okay? Because only when you use good ones that can have really high prediction power, then your prediction might be more accurate, okay? Otherwise, it might not be as useful. So in our setting, okay, so I guess coming back to this regression to the mean concept is that once we standardize X and Y, okay, we are trying to explain the deviation of Y through the deviation of X. Okay, if X is a really good predictor, that explanation or interpretation might go really well. Okay, and if X is not, maybe not so much. Okay, so keep that in mind. Okay, why we think about the deviation in the first place. Okay, so on average, okay, I know we talked about two types of deviation, but one thing is interesting is that Y deviates from 0 less than X deviates from 0. Okay, this might sound a little bit not very intuitive. Okay, but let me put it into the regression to the mean equation. That's the linear regression line that we're going to learn about. And I tried to tell you a little bit more of why that is the case. Okay, so the linear regression line that we will introduce, okay, later on we're going to introduce it in the original units. Okay, right now we're introducing it in the standardized units. Okay, meaning that, so that's what the SU stands for. Okay, standard units. Okay, so if you standardize Y and X, okay, it turns out that linear regression line that we're able to build, okay, has this linear relationship. Okay, and what we mean by that is that the standardized Y, standardized units, Y in the standard units will equal to R times the X in the standard units. Okay, so there are many like complicated math behind all of this, and we don't want to bother you about all of this. So here, the really interesting and important idea for us to grasp is that it is this linear relationship that we're trying to express over here. Okay, and then that is why we call it a linear regression. Okay, but right now we're presenting everything in terms of the standard units. Okay, so that's why we have the parenthesis SU everywhere for Y and X. Okay, and R, if you remember, is our old friend correlation. Okay, so what this is saying, okay, let me see. Yeah, So what this is saying is that if we are able to standardize X and Y, okay, then the linear regression that we're going to fit is essentially this equation. Okay, and then of course you might be wondering, okay, like how can I compute the correlation? We talked about it before, so you should know that. And then how can we re-express this regression line in the original scale? So that's another thing we're going to talk about. Okay, but what we're doing here again is that zeros, okay, for X and Y after standardized units, they're the mean. Okay, so this regression line is on the standard units scale. Okay, and we definitely highlight, okay, it's not true for all points. Okay, this is only on the average. And that's what you will see later when we do a linear regression prediction. It's not that the prediction is going to be perfect. Okay, because at the end of the day, we're still talking about the means. Okay, this linear relationship is about the means. But every time for every record, you will have some error going on. Okay, and then what we're trying to do is that later in next lecture, I think you'll learn what we mean by the linear regression is that we're trying to minimize the errors. Okay, minimize the function of the error so we can fit the best regression line. Okay, but once you do that, what you're essentially doing is that we're trying to specify a particular linear relationship between the standardized X and the standardized Y. Okay, and in particular, the correlation is the multiplication effect going on over there. Okay, and the correlation, once you know X and Y, you will be able to compute it. So that might be really straightforward to do, okay? But remember, this regression line that we're presenting over here is only on the standard units, okay? And what we're saying is that this is not true for every point, okay? In fact, probably not for any point unless you're exactly on the regression line, okay? Otherwise, you're always gonna get some error, but that's fine, okay? Because no prediction is perfect, okay? And what we're trying to express is the relationship between the averages of the X and Y's in their standard units. Okay, and then lastly, I hope once I present this line, it makes more sense of what we're saying in this sentence. Okay, on average, Y deviates from 0 less than X deviates from 0. That less than is coming through this R. Okay, so R, if you remember, the correlation coefficient is always between -1 and +1. Okay, and then the closer it is to +1, the higher, right? The positive correlation, right? The closer it is to the -1, the higher it is of the negative correlation. But if R is close to 0, then that's indicating like very little correlation going on. Okay, so and also just to recall that correlation is talking about linear relationship. Okay, and that's another reason if you think about, oh, why are we really talking about linear regression over here? Because R is measuring the linear correlation. Okay, the linear relationship. Okay, so what we're really talking about is the linear relationship over here. And the less than is because this will never go up above 1. Okay, So if you're looking at standard units over here, then it's always the absolute value of this is always bounded above by 1. So if you think about it, this is saying that the left-hand side, the y in SU, will deviate less from 0, okay, compared to the right-hand side, x deviate from 0, because there's a multiplication effect of less than 1, okay, multiplying over here. Hopefully makes sense. Might still be a little bit confusing, maybe at this stage of all of the math that we're talking about. Quick comments, questions? We'll give more examples coming up. So hopefully, and then a demo. So hopefully everything will become a little bit easier. But don't worry too much at this stage if you think that the regression to the mean, the expression that we're giving just now, a little bit complicated or challenging. I think the key takeaway there is that we're expressing everything in standard units. Okay, and that's how we express the linear relationship over there. But then, of course, a lot of times we care a little bit more about in the original units. Okay, so let's now bring it back to the, and the way to do that is, well, as you know, we can always mathematically write out that linear relationship in their original units as well. So we're going to see how that can be done. And then to talk about two very important concepts in linear regression is the slope and the intercept. Okay, so whenever you're fitting a regression line, like you have a cloud of data, a linear regression line going through it, going through the cloud of the data. So we care about how that straight line intersects with the y-axis. Okay, so that will give you the intercept. Okay, and then it will also we're thinking about the slope of that straight line, because that also tells us, I guess more importantly, that one tells us how the change of x is affecting the change of y. Okay, all right, so this regression line equation, okay, in the original units, okay, the regression line has this equation. Okay, so bear with me a little bit. Okay, it does look a little bit complicated, but if you remember what we just did in the previous small topic, on the left-hand side we have y in their standardized in the standard units, right? And on the x on the right-hand side we have r times x in the standard units, right? So really, right now, what we did is only to express the standard y and x in standard units using mathematical expression of how you can get them in the first place. Okay, so the left-hand side, remember, is the y minus the average divided by its standard deviation. So that's, you know, the y in the standard units. Okay, and then the right-hand side, we still have the r, the correlation. Okay, multiplies with the given x minus its average divided by the standard deviation of x. Okay, so that's what this is. Going back to the linear regression line we shown earlier in the standard units, but right now we're putting everything in the original units. Okay, and this is important because later on you will see that now if we're able to work with their original units, we're able to compute the slope and intercept easily. Okay, and then we can also interpret them in the original units, and that in a lot of cases probably will be a little bit more appealing. Okay. So, so that's what we mean just now. Okay, so this is the estimate y in standard units. Okay, the x in the standard units. Okay, and then the little r over here again is our correlation. All right, so pretty much the slope and intercept that we're going to introduce is just to trying to express this equation. Okay, using a particular way. All right, so y, okay, the estimated y in its non-standard units, okay, in its original units, okay, gonna be what we mean by slope times the x in its original units plus the intercept. Okay, and this is because mathematically we know that if we're going to fit a linear regression line through a cloud of data point, like I said, okay, that straight line, the intercept of it with the y-axis is going to give you the intercept, okay. And then the slope of it will give you the slope, okay? And for us, once you know the intercept and the slope, you can uniquely determine that straight line going through the data point, okay? And then that is how later on we're gonna do the prediction, okay? So again, the lines can be expressed by slope and intercept, and this is any straight line, okay? Even if you're not trying to fit a regression line that we're talking about, if you just like in math courses, if you ever try to just think about how to express a straight line, you always just have an intercept and slope as well, okay? And for us is that we're trying to put this into the concept of doing data science, okay? And more importantly, how the intercept and the slope can be interpreted in our context. Okay, so this is, I guess, what's new from there. But regardless, keep in mind that the regression line can always be expressed in this way. Okay, and for us, we are focusing what x is, what y is, and also how the intercept and slope can be calculated. So we're able to start doing predictions. Okay. All right. So in the standard units, okay, so this is the regression line that I'm talking about. So again, once you do standardization, remember everything will be, you know, this line going to go through 0, okay? And also all of the units, as you're seeing over here, like we're trying to use like 1, 2, 3, et cetera, okay, to show you the standardization. And all of the dots, okay, over here, just so you know, like on the left-hand side, they're just the standardized values of each data point. Okay, so we're showing 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we're showing 8 dots over here. Okay, and then this regression line, as you can see, okay, is centered at 0, 0 is because we standardized x and y. Okay, you will go through the 0, 0 line. Okay, and the slope of this line, of course, is the r that we're talking about earlier. Okay, it will be the regression coefficient. Okay, so if you take, like, say this, okay, so if you're taking, sorry, x as 1 unit, okay, then the height of that point will give you the r, okay, which is the regression coefficient. Oh, sorry, the correlation coefficient. Okay, so this is before we introduce everything on the original scale. Okay, but in the original units, okay, now you see that we don't have you know, 0, 0 anymore. Okay, but it's going to go through the average of x and average of y. Okay, that's what the regression line is supposed to go through. Okay, and that's why on the standard units, if you remember, because the mean, the average x and average y, there are zeros. That's why it's going to go through 0, 0. Okay, and then on the right hand side, if we come back to the original units, okay, so remember, this is before doing any kind of standardization. Okay, that's why if you think about the slope over here, okay, what you're doing is that, well, you have to think about the height whenever you're looking at one standard deviation of x. Okay. And you see that we don't write r specifically, we write r star because it won't be exactly the correlation coefficient that we know if we're able to do it on the standardized units. Okay, so again, nothing really changes. If you look at the positions, okay, of all of the dots, they're exactly the same, okay, compared to the standard units. And that is because, and I think we demonstrated that before in the demo, that if you do standardized units, like the relationship between the two variables won't change. Okay, you're really just standardizing it into each standardized units format. But where they're going to stay, say like on a graph, if you like on the right hand side, we pretty much just took out all of the units, right? We're just like putting it in a particular way so we can mimic, okay, what we really mean by if we have a straight line, okay, in the standard units that we understand as the like r, the correlation coefficient is the slope going on, then it's the equivalent to the original units where you go through the average of x and y, okay? But at the same time, you're gonna have a slightly different slope because it won't be correlation coefficient exactly, but it will be a factor of it, okay? So this is why, so again, the left-hand side is in the standard units, that's how we introduce it in the first place, okay? Y standard unit equals to R times X standard units, okay? And that's what this left-hand side is about. Our right-hand side is from the manipulation that we just did, expressing everything in standard units now using the original units, okay? And that's why in the earlier slide, if you remember, we have this a lot more complicated expression, okay, going on, okay? But at the end of the day, like I said, it's really just re-expressing the standard units version, okay, using the original units, okay? So this graph is trying to show you how they work in practice, okay? And then standardization, doing the standard of turning variables into standard units wouldn't really change like the relationship between them, okay? And then that's why it's feasible for us to think about the regression line first on the standard units, okay? And then turn it back into the original units. On the standard units, I hope everything is a little bit more easily interpretable, okay? Because we have y equals to r times x, okay? Go through the 0, 0 point, okay? And then that is how this straight line can be expressed, okay? However, once we come back to the original units, we got rid of the two x's going on here, okay? Because we don't really know what the values they are, okay? They are just in the general original units in this case. and then it's still the same straight line, okay? And then we just need to be a little bit more careful about the calculation of all of the other items over here. Okay, makes sense, hopefully? Okay, yeah, feel free to stop me typing questions in the chat, and we'll also have some chance to do breakout room discussion, okay? All right, so lastly, okay, the estimate, okay, of y, like I said, in the original scale, right, is the slope times x plus intercept, okay? So here, we're giving you the slope of the regression line of using a mathematical notation, okay, r times sd of y over sd of x. Sd stands for standard deviation. And the intercept of the regression line here, what we're saying is that it is going to be the average of y minus the slope times the average of x, okay? So with that in mind, with that in mind, I do want you to maybe chat with your neighbors. I'm going to create a breakout rooms in a second. And the task for you is that what we have covered so far actually can help us derive why the slope of the regression line is this and why the intercept of the regression line is this. Okay, so since we talked about it multiple times between the standard units and the original units, okay, and I was talking about it, I really hope you can take the chance and then think it through before we move on with the demo, and then just to show you how this calculation can be done using Python. Okay, but in the breakout rooms that we're gonna create in a second, please discuss with the neighbors. So feel free to go to topic 25. Okay, so my question here is that this is on slide 7. Okay, my question is, based on what we have covered in the previous slides, can you convince yourself that the slope of the regression line is indeed r times sd of y over sd of x? Okay, and then also the intercept of the regression line is indeed the average of y minus the slope times the average of x. Okay, so please, based on your understanding so far about the regression line, how it is constructed in the standard units, and then later on in the original units, how can you make sure that this is indeed true? Okay, so once that's covered, I think, discussed, then all of us will feel comfortable going into the demo, because in the demos, you could imagine we have expression for them, right? So we can just write function to calculate them. But it's very important, I think, to get the understanding well in the first place of why it is the case that the slope and intercept are calculated in this way. Okay, so again, it's on page 7. Okay, so that's the question itself, but the previous pages, all of the expressions might be useful for you to discuss why and convince yourself that that is the case. Okay, so I'm gonna pause record. Okay, so let me share my screen again. Okay, so the question for all of you in the breakout room is how to convince yourself that the slope of the regression line and the intercept of the regression line is indeed, okay, the way that we have presented them over here. So anybody wants to volunteer to share with us all what you have discussed in the breakout room? Did you find it, like, were you able to convince yourself this is true? And if so, how did you do that? Or if the discussion actually generated more questions, and definitely feel free to say it now, because we do have a lot of time to, I think, explain all of this, because that's the only topic for today. Okay, anyone wanted to give it a try?
Sure.
Thanks.
So
yeah. Let me know which slide I should go to.
Maybe 7.
Oh yeah,
or the discussion, or sorry, 8, the discussion question.
Oh, okay, you went ahead. Okay, alrighty. Yeah, we can talk about discussion question. Yeah, go ahead.
Oh, I thought you wanted us to talk about the discussion questions. Oh, my bad.
Oh, never mind. Okay, let me see. Okay, okay. No, that's good. So discussion question was discussed. Okay, so maybe, okay, that's great.
Yeah, we were just trying to figure out like what the units would be. So for R,
yeah,
because it's a proportion, we thought that didn't have any units. The slope, again, because it's multiplied by R, and then it's the standard deviation of X divided by the standard deviation of Y, I think, then those two would cancel. So we think the slope also doesn't have any units, and then the intercept, because it's the, what we predict to be Y, it would be dollars to be the unit.
Yeah, let's see. Okay, so let's talk about this first. So I'm not sure if every group got the chance to discuss the discussion question, but maybe we can talk about this quickly first, and then we can come back to this line, okay? So what Xiao was saying is that this discussion question is suppose we're going to use linear regression to predict, okay, so the outcome, okay, is in dollars, okay, is the candy prices, okay, from sugar content, which is in grams, okay. And then the question is, we're asked the units of each of the following, okay, R, the slope, and the intercept, okay. So just like what Sha was saying, it's important to come back to see what is the slope, right? How the slope is expressed, and then how the intercept is expressed, and then R, okay? So R, so like the first part, okay, R, because it's the correlation coefficient, okay? And that should have no units at all, okay? And so for R, I guess it's relatively more straightforward. And just remember, like, if we talk about R, remember we talk about it between -1 and +1, right? There's no like real units about them, okay? So that's another reason or another way to think about it, why we say that R does not have a particular unit, okay? Let's see the slope, okay? So the slope, if we come back to this, okay? So we know that slope is defined to be whatever we're multiplying with X, okay? And then the mathematical expression of it is the R, which has no unit. Okay, so that's probably, we don't need to worry about it. Standard deviation of Y over standard deviation of X. Okay, so I guess, Sha, what you were saying earlier is that because the standard deviation of X and the standard deviation of Y got canceled as well, so there's no unit for slope either. Would everybody agree? Or there's any kind of concerns or comments about that kind of line of thinking? What are standard units? What are the units of standard deviation in general? So the candy prices, which are the Y's, okay, they're the outcome, okay, they're in dollars, okay, and the sugar content is in grams, okay, so that's the X, okay. So we know that the mean, okay, the mean of Y going to be in dollars, right? Because this is the average of the candy price, okay? And the mean of the sugar content going to be in grams. What about their standard deviations? Do they have no units? Or if they have specific units going on as well? Anyone? Or maybe this is indeed a good, I know, like I said, maybe not every team got the chance to talk about the discussion question. And since we started on this already, maybe just to make it more efficiently, let me stop share. And then, yeah, I guess just the question is, what are the standard, like the units of standard deviations? And then from there, we can determine the unit of slope, okay, in this particular case. And then of course, you can also discuss about the intercept. So let me actually bring you back to the breakout room. So let's do this. So let me start. Okay. Definitely looking forward to having all volunteers talking about this. Okay, so yeah, we can start with the discussion question first and then move back to that two expressions. So I guess the remaining question just now is, because slope, okay, we know is R times the ratio of the two standard deviations. Okay, so the question becomes, what are the units of standard deviations of X and Y in this particular question? Okay, are they indeed canceled out, or do they have their own units? So the slope actually going to have a specific unit going on. Okay, anyone based on your discussion just now or maybe earlier? Are there units for standard deviations? Anyone? Thoughts or questions? All right, let me see. Kind of, okay. All right, so maybe in the chat, if you don't mind, okay. If you think they're, okay, let me just ask, I guess, a quicker question. So if I look at this, let me just look at Y, okay? So Y is the candy prices, okay, in dollars, okay? So my question for you is that, what's the unit of it? Is it no units, or is it dollars, or is it anything else? If you don't mind, if you can type in the chat so we can get the discussion rolling. And again, don't feel bad if you got the wrong answer. I mean, this is really helpful. And now I guess, because nobody volunteers, I guess this might not be an easy question. So it's pretty important for us to talk it through. So do you think there's like, you can type in no units, or it's in dollars, or it's something else? If you can type in the chat so we can get this rolling and we can continue the discussion. Anyone? Any thoughts? What would be the standard deviation of of candy prices. While we're waiting, let me see. I'm pretty sure we had I hope I can find it. Sampling, variance. Okay, maybe it's here. Topic 20, okay, where we talked about the mean and the standard deviation, okay? So that might give us some hint, I hope. Okay, standard deviation. So maybe later on you can check that out as well, okay? How far? Okay, all right. So standard deviation measures roughly how far the data from their average, okay? And it is the root mean square of deviations from average, okay? I guess the last item does show us, okay? Standard deviation has the same units as the data, okay? So of course, I mean, this is what was told to you. So maybe you still have confusion of why exactly that's the case. So standard deviation, if you remember what we computed, is that we compute the variance and then we take the square root of that, okay? And the variance is the square. If you remember, the variance is that we add, so we look at each observation of X, right? Okay, or Y in this case. Let me come back to this, okay? Like candy prices, okay, in dollars. So this is the Y, okay? So in practice, when we do standard deviation calculation, what we do is that first of all, we compute the variance, okay? Where we actually look at each Y from its mean, okay? We'll look at the distance, okay? We take the squared, okay? And then we take the sum and divide it by number of observations, okay? So it's the square, like average of the square distance, okay? So if you think about that, then variance actually has the units of dollar squared. Okay, it doesn't really make sense, but it's squared of dollars because of the fact that Y has a unit of dollars, okay? So the reason why people like standard deviations, if we come back to topic 20, is indeed that not only is interpretable, like telling us like on average, right, how the data are from their average, okay? But also it has the same units as the data. So it's really easy to interpret, okay? And another way to recall, I guess, is that if you remember the 68, 90, 95, and 99.7 rule that we've been talking about the normal distribution, okay? So remember, we're talking about like, say, within one standard deviation from the mean, right, we have 68% of the data, okay? And then within one standard deviation, what do? Is you mu minus sigma, right, to mu plus sigma, okay? So when you add and subtract mu and sigma, I guess that's another hint that they will have the same units, okay? So if the mean have the same units as the data, actually standard deviation also has the same units as the data, okay? So I guess coming back to all of this, so if we come back to the slope here, okay, so slope is R times SD of Y over SD of X, okay? R has no units, okay? But then SD of Y in our example has the units of dollars, okay? And then SD of Y has the units of grams. Okay, so the slope actually has a unit, which is, I guess, dollars over grams. Okay, okay. So the last one, the intercept. Okay, what Shell was saying earlier is that we'll have the a unit of the Y. Okay, which is the dollars in this case. Okay, so because again, the intercept is average of Y minus the slope times average of X. Okay. And so, of course, I mean, first of all, those two, they need to have the same units in the first place. Okay, so that's another reason, if you think about it, that slope does have some kind of units going on because the average of Y is in units of dollars, right? Average of X is in units of gram. So in order to bring slope times average of X to have the same units as average of Y, slope does have to have the units of, you know, dollars over grams. Okay, so this is a little bit complicated. Like I said, I guess this discussion did let me know at least that the units of the standard deviation were not as clear as we hoped it would be. So hopefully this discussion is helpful. And then I guess lastly, if you got the chance to discuss this expression of the two, I hope you're able to recognize that the way that we're computing all of this is like the slope, right? If we come back to here, right? Slope is what? Slope is whatever you multiply with X, okay? So if you come back to this regression line in the original units, okay? And so you see that here R times SD of Y, okay, divided by SD of X, that will be the ultimate ratio that you're multiplying with X, okay? So that's why slope is, so it's a little bit math going on. So like I said, left-hand side is estimated y in standard units, right? Right-hand side r times x in SU. So, but then we express the y and x in their standard units using their original units, okay? So then you're left with like estimated y, average of y, SD of y. So once you do the math, rearrange the terms, you will see that the slope is indeed r times SD of y over SD of x. Okay, so that's what we're hinting in terms of why this is the case. And then the intercept of the regression line is going back to this, okay, to this expression. And then we're able to get the intercept in this average of y minus slope times average of x. Okay, so again, hopefully it's not too tricky. And I think it's important to think about everything in terms of the standard units first, okay? And then we come back to the original units using some kind of algebra, okay? And that's exactly how we compute the slope and the intercept, where we come to this 2 formula, okay? And then of course the discussion question, I guess we jumpstart on the discussion question, so that's useful for us to think through what are all of those items are. So to wrap up for today, I just want to do a quick demo to show you, well, in practice, how you can calculate the slope and the intercept, okay? And then in Python. And again, in this slides, we already talked about the mathematical formula for both of them, okay? So in practice, as you will see in the demo, we wrote functions of like calculating the R, calculating the SD of both, and then we can get the slope, okay? And then for the intercept, we really just need to get the average of Y and then the average of X. Once we compute the slope, we're able to compute the regression, we're able to compute the intercept as well. Okay, so everything, the theory is in the slides itself, okay? So in Python, what we're doing is that we wrote functions, okay, based on this formula, and then we're able to perform this calculation, okay? All right, so without further ado, let's come to this only demo for topic 25, okay? This is what we call slope and intercept. That's how to compute it, okay? So you see that up front, okay, I wrote 4 different functions here. The first one is what we have seen before, okay, just to get the standard units, okay, because it's important, as you can see, to get all of the computation going. So this is, again, for any data that you pass into this function, you take the difference, right, between every data point from its average, okay, and then divide it by its standard deviation, okay? So then the output of this is going to give you the x in its standard units, okay? And the correlation is another thing that we talked about last time, okay? So again, what we're doing is we have the table passed in, the 2 labels that we want to compute the correlation with, okay? So what we're doing, if you remember, is that we get the standard units of label x times the standard units, which is what we had written earlier, of y, and then we take the mean that will give us the correlation. Okay, so this is from before, okay? The new things here is how to compute the slope and the intercept, okay? And then what we're doing, like I said, is directly following this 2 formula, okay? The slope, remember, is r times SD of y over SD of x. So what we're doing is we pass the table, right, the label of x and label of y, okay? What we do is that first of all, we compute r as the correlation from the correlation function that we wrote, okay? And then the second is, well, we get the r times the standard deviation of y, right, over the standard deviation of x, okay? So nothing fancy, it's really just following the formula that we covered. And lastly, the intercept, if we come back to the expression, is the average of y, right, minus slope times the average of x. So once you have the slope, right, what you do is you get the average of y, right, minus the slope times the average of x, and then you will get your intercept. Okay, the input again is t and the 2 labels. Okay, so again, notice that we always try to do everything in terms of data table, okay, because, well, we're really talking about like 2 columns of our interest, right, and then we're trying to compute, like say regression, like linear regression, slope and intercept. So it's always good to put everything, I think, in terms of data table. All right, so let me load these functions and our Galton data. Okay, so again, here I'm naming it mid-parent, and then that's the child height. Okay, so again, we don't deal with father's height and mother's height specifically. Okay, we look at their mean because we are using that as the predictor. So this is just a really simplified like x and y going on here, so we can see in action how the tables are doing. Okay. All right, so this one is what we reviewed earlier today, that how to do the nearest neighbor prediction, okay? The nearest neighbor, we now call it like NN, nearest neighbor, okay? And that's not a not a linear regression, okay? That is really just like the practice. If you remember, we get the mid-parent's height in a particular range, right? And then we take the average of them as the predicted value for the child's height, okay? So here we're refreshing and using this, recalling this, because we can use this as a comparison as what we're gonna do linear regression prediction as well, okay? So keep in mind, and if you remember from this lecture here, it's not on a straight line, right? The prediction is close, okay? When we do in the nearest neighbor prediction, okay? It's close to a straight line, but not exactly, okay? However, later on when we're doing this prediction with the linear regression, you will see something slightly different, okay? All right, so this is, whatever I did up here is just doing the nearest neighbor prediction, okay? So let's keep that first, okay? And then now, we know that now we have our X as the mid-parent, right? Y as the child height, okay, all of them. So we're able to, in this case, get the slope and intercept running, okay? And then what we do is, again, we roll the slope and the intercept functions up here, okay? So we're just calling those functions on the heights table, right? And then we clearly label those variables that we're working with. So the X label is the mid-parent, the Y label is the child. So when we do both, okay, here, we get a slope of 0.637, and then the intercept is 22.64-ish, okay? So this is computing them, okay? And lastly, we can use this, okay, the slope and intercept, right, to make predictions, okay? And what we do is, so first of all, let's see. We first of all get the mid-parents where they're a particular height, okay? And then what we do is that the prediction, as you can see, so I probably need to slow down a little bit here. What we're doing is that we have the heights, okay? We get the regression prediction. Okay, sorry, we are adding it as a new column of the regression prediction, okay? In particular, we get the slope that we computed earlier, okay? We multiply that with the height of the mid-parent, okay? And then we plus the intercept, okay? So the prediction is exactly this line, okay? And that's what we're writing over here. Estimate, or the predicted value of Y, okay, is the slope that you computed times X plus the intercept, okay? So for us, if we have computed the slope, which is about 0.64, and then the intercept, which is about 22.64, then we're able to use them to make predictions of all of the mid-parent that we have, like in the table that we have, okay? And what we do is we use the with column method, okay, to add a new regression prediction, okay? And that prediction is done by slope times X plus intercept, okay? So that's what we mean by the regression, and the prediction. So let me do that. And lastly, I want to show all of the two different types of predictions that we have done, okay? So the darker blue is still the actual observed child's height, okay? And then the nearest neighbor prediction is still in the yellow color, okay? And the regression coefficient, the regression prediction that we're doing over here is the lighter blue, okay? So with the remaining 5 minutes, I want you to go back to your breakout room and discuss a little bit of the differences and I guess similarities between the two types of predictions. Okay, so remember the yellow one is the average nearest neighbor prediction. Okay, and that's what we had done before. We reviewed a little bit today as well. And the regression prediction is following the regression line that we have presented. Okay, we compute the slope. Okay, we compute the intercept. And then we're using exactly this line, this expression to do the prediction, okay? So here in this graph, we have seen these two types of predictions, okay? They're similar to some degree, but they're also different from each other, okay? So I would like you to go back to your breakout room. And again, yeah, I guess, yeah, I'm not sure how easy it is because you have to run, I guess, this demo to replicate this exact graph. So I'm not too sure how easy it is. So maybe, okay, let me give you 1 to 2 minutes, maybe just here to think about, so you can still view it. And then we can wrap it up as a way to discuss how the different predictions are working and how Like, do you have a preference of the two? And if so, why? That kind of questions will be pretty open-ended. Okay, so the question here is, what are the differences and the similarities between the two types of predictions, what we're seeing on the graph, and why do you think they are similar, and why do you think they're different? Okay, so maybe 1 to 2 minutes-ish, and then we can wrap it up.
Oh, you're still showing your screen.
Oh yeah, right. Sorry, maybe I was not clear. Yeah, I was saying that I'm just showing the screen because once I put you in the breakout room, you won't be able to see it.
Oh, okay.
Yeah, because this is right. You're right. So yeah, so okay, yeah. Since there are only 2 minutes, so maybe you're left, we can maybe talk about it. So what stands out, I guess, between the two predictions based on what you're seeing over here? Immediately, like they're pretty close, right, to some degree. Okay, that's one thing. And again, we know that both of them are they're regress to the mean. Okay, because both of them are based on mean. It's mean-based prediction. Okay, so maybe that's not too surprising. And to me, I think one thing really interesting, I guess the similarity is that they're close. Okay, but not exactly the same. Okay, so difference over here is that the regression prediction, like I was saying earlier, is that it's going to be a straight line. Okay. And it's going to be a straight line because if you look at this relationship, right, it's a given slope for any x, right, plus the same intersect everywhere. Okay, so for any x, you have the same slope, okay, plus the same intersect. So it's not surprising that it's going to be a straight line. Okay, and that's indeed, if we come back again to this discussion, okay, is that this is exactly like that linear relationship that we're talking about. Okay, so in that sense, I think the prediction turns out to be a straight line is no surprise. Okay. On the contrary, if we look at the average neighbor prediction, okay, we know that they're not exactly the straight line, right? And maybe it's easier to read here. Okay, there's some wiggling up and down. Okay, so this is again the main difference to me that is between the nearest neighbor prediction and the linear regression prediction. The linear regression prediction will be a straight line, okay, whereas the nearest neighbor prediction might not be, but they could be close, okay. And if you remember what we were talking about at the beginning part of today's lecture, we're saying that if the correlation between x and y is pretty high, okay, or pretty close to +1 or -1, okay, then those points, the predicted points that we're going to do could be very close to a straight line, okay. So, but on the contrary, for linear regression, by definition, it's going to be a straight line. Okay, so that's important to note. And they're similar, just looking at the, I guess, the magnitude, like how close they are. And also, I think the main reason of why they're similar is both of them are based on mean prediction. Okay, slightly different method, of course, but regardless, we always see the regress to the mean effect, right? Like say, you can have all kinds of variability of the observed between the predicted, but what the predicted is trying to predict for is on average how you're going to behave. Okay, so that's why whenever you're doing prediction, or even just imagine like a regression line going through a data, like a data cloud, you will never match every data point, right? You can only do as best as you can, and it's no problem at all. Okay, the method itself is built on average. It's not about each particular observation. Okay, so as long as the averages overall work well, then everything should be good. Okay, all right. I know we're running out of time, so I'm gonna maybe end here. And again, feel free to stay over if you have questions about, I mean, today's lecture or the final project or your individual project too. Okay, that is due later this week. So make sure that you